Welcome back, fellow explorers. Somewhere in the darkness right now, a telescope the size of a tennis court is floating 1 million miles from Earth, colder than deep space itself, staring into the ancient light of the universe. It has been doing this since Christmas Day 2021, and what it has found has changed everything we thought we knew. This is the James Webb Space Telescope, and these are 50 facts that will leave you breathless. A Christmas launch. On December 25th, 2021, while most of the world was opening presents and sitting around holiday tables, a rocket rose from the Guiana Space Center in South America and carried into the sky the most ambitious scientific instrument humanity has ever built. The James Webb Space Telescope, 25 years in the making, $10 billion in cost, involving the work of thousands of engineers, scientists, and technicians from 17 nations, launched on Christmas morning. It was, in every sense, a gift, not just to the astronomers who had spent careers waiting for it, but to every human being who has ever looked up at the night sky and wondered what was out there. The rocket worked perfectly. The telescope separated cleanly, and the universe, for the first time, had a truly worthy eye. 1 million miles away, Webb does not orbit Earth like the Hubble Space Telescope. It orbits the Sun at a special gravitational balancing point called Lagrange Point 2, located approximately 1 million miles from Earth in the direction directly away from the Sun. At this location, the gravitational pulls of the Earth and Sun combine to keep Webb in a stable position, orbiting the Sun at the same rate as Earth, but always staying roughly 1 million miles behind us. This means Webb can never be serviced by astronauts. It is too far away for any crewed mission to reach. It was designed, from the very beginning, to work perfectly on its own. Everything had to go right. And almost everything did. 18 golden mirrors. The primary mirror of the James Webb Space Telescope is not a single piece of glass. It is an arrangement of 18 hexagonal segments, each coated in a microscopically thin layer of gold. Together, they form a mirror 6.5 meters across, nearly the width of a two-lane road. Each segment is made of beryllium, a lightweight metal chosen for its ability to hold its shape in the extreme cold of space. The gold coating was applied because gold reflects infrared light, the wavelength Webb was designed to see, more efficiently than any other material. Each segment had to be aligned with every other segment to within a fraction of the width of a human hair, using tiny actuators that could adjust their positions with nanometer precision. The result is the most precise large mirror ever placed in space. Colder than deep space, Webb operates at temperatures that are almost incomprehensibly cold. Its main instruments are chilled to approximately minus 233 degrees Celsius, just 40 degrees above absolute zero, the theoretical coldest temperature anything in the universe can reach. In fact, parts of Webb are colder than many regions of deep space itself. This extreme cold is necessary because Webb observes infrared light, essentially heat radiation. And if any part of the telescope were warm, its own heat would blind its instruments, like trying to see stars through a sky full of floodlights. A large sunshield the size of a tennis court keeps the Sun, Earth, and Moon permanently behind the telescope, allowing the instruments to cool to these extraordinary temperatures through passive radiation alone. The sunshield. Webb's sunshield is one of the most remarkable engineering achievements in the history of space exploration. It consists of 5 layers of a material called kapton, each thinner than a human hair, stretched across a structure the size of a tennis court. Each layer reflects and radiates away the heat from the Sun. Together, the 5 layers reduce the temperature from approximately 85 degrees Celsius on the sun-facing side to minus 233 degrees Celsius on the cold side, a difference of over 300 degrees across just a few meters of space. The sunshield had to be folded origami style to fit inside the rocket, then unfurl perfectly in space through a sequence of 178 individual release mechanisms, every single one of which had to work correctly. They all did. The 178 single points of failure. The deployment of the James Webb Space Telescope after launch was one of the most nerve-wracking events in the history of space science. Over the course of 2 weeks, the telescope had to perform a complex sequence of deployments, unfolding its sunshield, extending its secondary mirror, and locking its primary mirror segments into place. This sequence involved 178 individual mechanisms that each had to function correctly. If any single one failed, the mission could have been compromised beyond repair. Engineers called these single points of failure. There were 178 of them. Every one worked. When the last mirror segment locked into place and the telescope's systems came online, scientists at the Space Telescope Science Institute in Baltimore, 6 times more powerful than Hubble. The Hubble Space Telescope, launched in 1990, transformed our understanding of the universe. Its images of galaxies, nebulae, and deep space became some of the most iconic photographs in human history. Webb collects more than 6 times as much light as Hubble. Its mirror is over 2.5 times larger in diameter, and it observes primarily in infrared, wavelengths of light that Hubble could only partially detect. This means Webb can see through the clouds of gas and dust that blocked Hubble's view, revealing what lies inside stellar nurseries, behind interstellar dust clouds, and at distances so vast that the light has been traveling for billions of years. Hubble showed us the universe. Webb is showing us what Hubble could not see. Seeing back in time. When Webb looks at a distant galaxy, it is not seeing that galaxy as it exists today. It is seeing that galaxy as it existed when the light it is now detecting first left it, which could be billions of years ago. Light travels at approximately 300,000 kilometers per second. But the universe is so vast that light from the most distant objects Webb can detect has been traveling for over 13 billion years. When Webb observes a galaxy 13 billion light-years away, it is seeing that galaxy as it was just a few 100 million years after the Big Bang, when the universe was still young, when the first stars were igniting, and when the structures we see around us today were just beginning to form. Webb is not just a telescope, it is a time machine, the first light image. On July 12, 2022, NASA released Webb's first full-color science images to the world, and they were breathtaking. The first image, called Webb's first deep field, showed thousands of galaxies in a patch of sky so small it could be covered by a grain of sand held at arm's length. Some of those galaxies are so distant that their light has been traveling for over 13 billion years. The colors were not arbitrary. They were assigned to different wavelengths of infrared light to make the image comprehensible to human eyes. But the structures, the spirals, the ellipticals, the smears of gravitationally lensed light were real, captured by a machine that humanity had dreamed of building for decades, and finally, against enormous odds, succeeded. Broken cosmology. When Webb first turned its eye to the distant universe, it found something that confused and excited astronomers in equal measure. Everywhere it looked in the early universe, it found galaxies, large, well-formed, surprisingly massive galaxies that should not have existed so soon after the Big Bang. According to our models of how the universe evolved, galaxies grow slowly over billions of years as gravity pulls matter together. But Webb was finding galaxies that appeared to be as massive as the Milky Way, existing just a few 100 million years after the Big Bang. Some scientists joked that Webb had broken cosmology. The real answer is more nuanced. Our models needed updating. But the discovery that the early universe was far more active and structured than anyone expected is one of Webb's most profound contributions to human knowledge. Little red dots. Among the most mysterious objects Webb has discovered are what astronomers call little red dots, tiny, faint, red smudges appearing in deep field images from the very early universe. They were not predicted by any existing model. They appeared abundant, numerous, and strange. Scientists debated what they were for years. Were they dense collections of stars? Were they something entirely new? The leading theory, supported by Webb's most recent and detailed observations, is that little red dots are supermassive black holes wrapped in dense cocoons of hot ionized gas. These black hole stars, a concept so exotic it barely had a name before Webb, appear to be common in the early universe, and their existence challenges everything we thought we knew about how black holes and galaxies form and grow together. Glimpse 17775. In 2025, astronomers using Webb identified a particularly remarkable little red dot called Glimpse 17775. It existed about 1.8 billion years after the Big Bang, located behind a galaxy cluster called Abell S 1063. The cluster's gravity acted as a natural magnifying glass, amplifying the light from Glimpse 17775, so that 30 hours of Webb observation time was effectively equivalent to 80 hours. The result was the most detailed spectrum ever captured of a little red dot, over 40 distinct spectral lines, each one a piece of evidence. Hydrogen, oxygen, helium. 16 iron lines forming what the research team called an iron forest. All of it pointing to the same conclusion: a rapidly growing black hole wrapped in a dense, hot gas cocoon. A puzzle, finally assembled piece by piece. The iron forest. Within the spectrum of Glimpse 17775, astronomers found something they had never seen before in a little red dot. 16 separate iron spectral lines, packed so closely together that the team named them the Iron Forest. Iron lines in a spectrum are a signature of extreme conditions: high temperatures, high densities, and the presence of a powerful energy source capable of exciting iron atoms to produce that characteristic light. The only known process capable of producing such a feature in the early universe is a rapidly accreting black hole. A black hole consuming surrounding gas at an extraordinary rate, releasing energy that heats everything around it to temperatures of tens of thousands of degrees. The iron forest was not just beautiful data, it was a fingerprint. And the fingerprint pointed to something extraordinary. A planet where it rains rocks. Webb has revealed some of the most extreme weather in the known universe, on worlds orbiting other stars. One of the most remarkable is a planet where the clouds are not made of water vapor or ice crystals, but of silicate particles, essentially fine sand and rock dust, suspended in an atmosphere so hot that rock itself vaporizes. On the day side of this planet, temperatures are so extreme that silicates exist as gas. As that gas is carried by circulation to the cooler night side, it condenses into clouds. Those clouds then rain, not water, but liquid rock droplets, falling through an atmosphere of screaming hot gas. Webb detected this by analyzing the infrared spectrum of the planet's atmosphere with a precision no previous telescope could achieve. The first CO2 detection on an exoplanet. In one of its earliest science results, Webb made a historic first: the direct detection of carbon dioxide in the atmosphere of a planet orbiting another star. The planet, WASP 39b, is a hot Jupiter, a gas giant orbiting very close to its star. Webb detected not just CO2, but also water vapor, sodium, potassium, and crucially, sulfur dioxide, a molecule produced by photochemical reactions in the atmosphere, meaning sunlight from the planet's star is actively driving chemistry in its skies. This was the first time photochemistry had been detected on a planet outside our solar system. It transformed exoplanet science from a field of rough approximations into a field of genuine, detailed atmospheric chemistry, a transformation that will only deepen as Webb continues its observations. TRAPPIST-1 and 7 worlds. 39 light-years from Earth, a small, cool red star called TRAPPIST-1 is orbited by 7 rocky, Earth-sized planets, 3 of which sit within the habitable zone, where liquid water could theoretically exist. Webb has been systematically studying these 7 worlds, analyzing their atmospheres with unprecedented precision. The early results have been both sobering and fascinating. The innermost planets appear to lack thick hydrogen atmospheres, which rules out certain types of habitability. But the search continues. Each observation refines our understanding of what these worlds are like, and the possibility, not confirmed but not ruled out, that one or more of these 7 planets might harbor conditions suitable for life remains one of the most tantalizing open questions in all of science. Water vapor on Europa. Jupiter's moon Europa has long been considered one of the most promising places in the solar system to search for life. Beneath its icy crust lies a liquid water ocean, kept from freezing by the gravitational tidal forces of Jupiter. In 2023, Webb detected a localized plume of water vapor above Europa's surface, the clearest confirmation yet that material from that subsurface ocean is escaping through the ice and venting into space. The implications are profound. If water from Europa's ocean can escape to the surface, then the ingredients for life, if they exist in that ocean, could potentially be detected without ever needing to drill through kilometers of ice. Webb did not find life on Europa, but it took a significant step toward knowing where to look. A new moon of Uranus. In February 2025, astronomers analyzing Webb images made a quiet but remarkable discovery: a previously unknown moon orbiting Uranus. The moon, designated S/2025 U1, is tiny, estimated at just 8 to 10 kilometers in diameter, smaller than many cities. It orbits Uranus at a distance of about 57,844 kilometers, completing one orbit every 9.6 hours. Webb detected it because of its extraordinary sensitivity to faint infrared light. The moon is so small and so dark that no previous telescope had ever resolved it. It became the 29th known moon of Uranus. It has no name yet, but it exists, quietly circling a blue-green planet nearly 3 billion kilometers from the Sun, unknown until a golden-mirrored telescope floating 1,000,000 miles from Earth finally looked closely enough to see it. The interstellar comet 3I Atlas. In 2025, astronomers detected something extraordinary passing through our solar system, only the 3rd interstellar object ever observed. Comet 3I Atlas arrived from outside our solar system, whipped around the Sun, and began its long journey back out into interstellar space. Webb turned its instruments on this visitor with urgency, capturing its chemical fingerprint for the first time on any interstellar object. The results were astonishing. The comet was extraordinarily rich in carbon dioxide, far more than typical solar system comets. It contained methane gas, detected for the first time ever on an interstellar visitor, and its chemistry pointed unmistakably to a formation environment completely unlike anything in our solar system. This was not just a comet. It was a message in chemistry, written in a solar system we will never visit, traveling trillions of kilometers to be read by Webb. Methane from another star system among Webb's observations of Comet 3I Atlas. One finding stood out above all others: the direct detection of methane gas, the first time methane had ever been detected on an interstellar visitor. Methane is highly volatile. It sublimates, transforms from solid ice directly into gas at very low temperatures. Its presence in Comet 3I Atlas suggested that the methane had been buried deep beneath the comet's surface, protected from vaporization during its long journey through the cold emptiness between stars. Only when the comet swung close to our Sun did the heat finally penetrate deep enough to release the buried methane in a burst of gas. The amount detected was surprisingly high, far more, relative to water, than in any solar system comet. Chemistry from another star system finally revealed carbon dioxide rich beyond comparison. Webb's observations of Comet 3I Atlas confirmed something that had been suspected from earlier ground-based observations. This comet was extraordinarily rich in carbon dioxide. Most solar system comets release carbon dioxide, but in relatively modest amounts compared to water. Comet 3I Atlas released carbon dioxide at rates that dwarfed almost anything in our solar system, suggesting that wherever this object formed, conditions were dramatically different from the cold outer regions of our own solar system, where comets typically originate. The precise ratio of carbon dioxide to water, methane to carbon dioxide, and other molecular abundances are like isotopic fingerprints. They encode the temperature, pressure, and chemistry of the environment where this comet condensed billions of years ago, in a solar system orbiting a star whose name we do not know, watching gas shut off. As Webb tracked Comet 3I Atlas, moving away from the Sun after its closest approach, it observed something that sounds simple but is scientifically profound. It watched the comet's gas production decline in real time. As the comet moved farther from the Sun, the heat reaching its surface decreased, and the volatile ices that had been sublimating into gas began to freeze again. Water, being less volatile than methane or carbon dioxide, shut off its gas production first, dropping sharply as the comet moved beyond a certain distance. Carbon dioxide and methane persisted slightly longer. Webb captured this entire sequence with its mid-infrared instrument, essentially watching the comet go cold in slow motion. It was the most detailed observation ever made of an interstellar object's activity profile, a window into the physics of a world from beyond our solar system. Stars being born. One of Webb's most extraordinary capabilities is its ability to see through the vast clouds of gas and dust that shroud regions of active star formation, nurseries where new stars are being born. Hubble could only see the outside of these clouds. Webb's infrared vision penetrates straight through them, revealing the protostars inside. Stars in the earliest stages of formation, still wrapped in their birth cocoons of gas and dust, drawing in material from the cloud around them, heating up, beginning the slow gravitational collapse that will eventually ignite nuclear fusion in their cores. Webb has cataloged hundreds of these protostars that were previously invisible to any telescope. Each one is a sun in the making. Each one will, in billions of years, potentially have planets orbiting it, planets that may, one day, harbor the pillars of creation, reimagined. One of the most famous images in the history of astronomy is the Pillars of Creation, a photograph of towering columns of gas and dust in the Eagle Nebula, first taken by Hubble in 1995. Webb photographed the same pillars in 2022, and the result was a revelation. Where Hubble saw dramatic dark columns silhouetted against glowing gas, Webb saw through the dust entirely, revealing hundreds of newly forming stars embedded within the pillars themselves, stars that Hubble had never been able to detect. The columns that Hubble had shown us as dark and opaque were, in Webb's infrared vision, translucent, lit from within by the light of protostars. The same structure, seen by two different telescopes, showed two entirely different realities. It was a perfect illustration of what Webb was designed to do. Cassiopeia A in new light. Cassiopeia A is the remnant of a star that exploded as a supernova roughly 340 years ago, located about 11,000 light-years from Earth. Astronomers have studied it for decades, with radio telescopes, X-ray observatories, and optical instruments. When Webb turned its instruments on Cassiopeia A, it revealed something unexpected: structures and features in the remnant that had never been seen before. Delicate filaments, knots of material, regions of different chemical composition scattered across the expanding shell of stellar debris. Webb detected the fingerprints of specific elements: silicon, argon, neon, each telling part of the story of how a massive star dies and scatters the atoms it spent a lifetime forging into the space around it. In a very literal sense, Webb was reading the chemical biography of a dead star. The deepest infrared image ever. Webb's first deep field image, released in July 2022, is the deepest infrared image of the universe ever captured. In a patch of sky smaller than a grain of sand held at arm's length, it contains thousands of galaxies. Some of those galaxies are so distant that the light reaching Webb left them when the universe was less than 1 billion years old. The reddest, faintest smudges in the image are not defects or noise. They are real galaxies, their light stretched by the expansion of the universe from the ultraviolet and visible wavelengths in which they originally shone, all the way into the infrared where Webb can detect them. The image is not just beautiful. It is a data set of extraordinary scientific richness, containing information about galaxy formation, dark matter, and the large-scale structure of the universe that astronomers will be mining for decades. Gravitational lensing as a magnifying glass. Throughout its observations, Webb has repeatedly taken advantage of one of nature's most remarkable phenomena: gravitational lensing. When a massive object, like a galaxy cluster, sits between Webb and a more distant object, the cluster's gravity bends the light from the distant object, acting as a natural magnifying glass. This effect can amplify the light from a background object by factors of 10, 20, or even more, allowing Webb to see things that would otherwise be far too faint to detect. The observations of glimpse 17775, the little red dot, benefited from gravitational lensing that effectively gave Webb the equivalent of 80 hours of observation time from just 30 hours of actual telescope time. Without this cosmic magnification, the most detailed spectrum ever captured of a little red dot would have been impossible. Galaxy mergers in the early universe. In 2025, Webb revealed a remarkable system of at least 5 interacting galaxies existing just 800 million years after the Big Bang, a cosmic traffic accident happening in the earliest chapter of the universe's history. The discovery showed that galaxy mergers and interactions, processes that today take billions of years to play out, were already happening in the young universe, far earlier than most models predicted. These early mergers are important because they drive the growth of galaxies and the black holes at their centers, mixing stars and gas and triggering bursts of new star formation. Webb's ability to observe such ancient events with clarity means that the story of how the universe evolved from a smooth sea of gas into the structured cosmos we see today is being rewritten, one observation at a time. Supermassive black holes in the infant universe. One of Webb's most consistent and striking findings is the presence of supermassive black holes in galaxies that existed when the universe was very young. A black hole confirmed by Webb in a galaxy just 570 million years after the Big Bang was already actively growing, consuming surrounding gas at a prodigious rate, shining brilliantly as a quasar. The puzzle is not just that it exists, but that it is so large. Growing a supermassive black hole takes time. Matter falls in gradually, and there are physical limits to how fast a black hole can accrete. For such a massive black hole to exist so early, it must have either started from an unusually large seed or grown faster than our models allow. Webb has found these objects repeatedly. The early universe was full of them, and we do not yet fully understand why. The first stars. Among the most important scientific goals of the James Webb Space Telescope is the search for evidence of population 3 stars, the very first stars that ever formed in the universe, igniting in the primordial darkness just a few 100 million years after the Big Bang. These stars would have been enormous, perhaps hundreds of times more massive than the Sun, and they would have burned brilliantly for just a few million years before exploding as supernovae, seeding the universe with the first heavy elements it had ever contained. No population 3 star has ever been directly observed, but Webb is searching, looking for the specific chemical signatures that would indicate a galaxy whose stars contain only the hydrogen and helium that existed at the beginning of time, with none of the heavier elements that came later. The search continues. A moon-forming disk around an exoplanet. In one of its most extraordinary findings, Webb provided the first direct measurements of a disk of material surrounding a large exoplanet, a disk that may be in the process of forming moons. The planet, a gas giant orbiting a young star, was found to be surrounded by a structured disk of gas and dust, similar in concept to the protoplanetary disk that surrounded our own sun when the planets of our solar system were forming billions of years ago. But this disk encircles not a star, but a planet, and the material within it could theoretically coalesce over millions of years into one or more moons. Webb measured the chemical and physical properties of this disk in detail for the first time ever, opening an entirely new area of planetary science. Stephan's Quintet. One of the most spectacular images released from Webb in its first science package was of Stephan's Quintet, a group of 5 galaxies located about 290 million light-years from Earth. 4 of the 5 are locked in a gravitational dance, repeatedly passing through and interacting with each other over billions of years. Webb's image showed the quintet in extraordinary detail. Vast plumes of gas being stripped from galaxies, shock waves where one galaxy is plowing through the others at speeds of millions of kilometers per hour, regions of intense star formation triggered by the collisions. In the center of one of the galaxies, a supermassive black hole is actively feeding, surrounded by a bright ring of hot gas. It was not just an image. It was a portrait of cosmic violence on a scale that defies imagination. The Carina Nebula's cosmic cliffs. Another of Webb's first release images showed the Carina Nebula, specifically a region at the edge of a giant cloud of gas and dust that astronomers nicknamed the Cosmic Cliffs. In visible light, this region appears as a dramatic but relatively simple boundary between a glowing nebula and dark dust clouds. In Webb's infrared vision, the scene transformed entirely. The dark dust was rendered semi-transparent, revealing hundreds of previously hidden young stars in the earliest stages of their lives, embedded in the cloud, glowing in infrared light. Jets of material were seen shooting from newborn stars, punching through the surrounding gas. It was one of the most actively star-forming environments ever imaged in such detail, a stellar nursery caught in the act of creation. The Southern Ring Nebula. A planetary nebula is the beautiful, glowing shell of gas expelled by a dying star, a sun-like star at the end of its life, puffing away its outer layers over thousands of years. The Southern Ring Nebula, located about 2,000 light-years from Earth, has been photographed by many telescopes. But Webb revealed something that had been hidden. At the center of the nebula, what appeared to be a single dying star is actually 2. A second star, dusty and dim, had been invisible to previous instruments. Webb's infrared sensitivity revealed it clearly, showing that the dying star's ejected material had been shaped by the gravitational interaction with its companion. The nebula's beautiful rings and shells were not just random. They were the product of a stellar relationship that ended in death and light, probing the atmosphere of a rocky world. One of Webb's most challenging and important tasks is determining whether rocky, Earth-sized exoplanets have atmospheres, and if so, what those atmospheres are made of. This is enormously difficult. A rocky planet is tiny compared to its star, and its atmosphere represents an almost vanishingly small fraction of the light that passes through it during a transit. But Webb's sensitivity is extraordinary. It has already constrained the atmospheres of several rocky exoplanets, ruling out thick, hydrogen-rich atmospheres on the innermost TRAPPIST-1 planets, and measuring the temperatures of rocky worlds with enough precision to begin distinguishing between planets with and without significant atmospheres. This is the beginning of the most important search in the history of science, the search for a world where the air might be breathable, an exoplanet's morning and evening. One of Webb's most elegant recent findings concerns the difference between the morning and evening sides of a tidally locked exoplanet, a world that, like our moon facing Earth, always shows the same face to its star. On such a planet, one side is in permanent day and one in permanent night, with the morning and evening limbs, the edges that face the transition zone, experiencing perpetual sunrise and sunset, respectively. Webb confirmed that these two limbs can have dramatically different atmospheric compositions and cloud structures. The morning side was cloudier. The evening side was clearer. This asymmetry, driven by the planet's atmospheric circulation, was exactly what models had predicted, and Webb's confirmation of it represented a triumph of observational astronomy matching theoretical physics with real data. An ultra-hot Neptune. Among the exoplanets Webb has studied is one called LTT 9779b, an ultra-hot Neptune, a class of planet so close to its star that its atmosphere is being stripped away, and its surface temperatures reach over 2,000 degrees Celsius. It occupies a region of planetary parameter space called the Neptune Desert, a zone so close to its star that most planets of this size have had their atmospheres entirely boiled away. LTT 9779b somehow still has a substantial atmosphere, rich in carbon dioxide and other molecules. Webb observed it in detail, revealing dynamic weather patterns in an atmosphere under conditions of almost unimaginable extremity. It is a planet that should not exist in the form it does, and its existence is telling us something important about the processes that shape planetary evolution. A gamma-ray burst from the dawn of time. In 2025, Webb confirmed the source of a gamma-ray burst, one of the most energetic explosions in the universe, that occurred when the universe was just 730 million years old. Gamma-ray bursts are produced when massive stars collapse into black holes, releasing more energy in a few seconds than the sun will produce in its entire lifetime. Webb's quick turnaround observations, taken just hours after the burst was detected by other telescopes, not only confirmed the explosion, but also detected the burst's host galaxy for the first time at such extreme distance. This was the most distant gamma-ray burst host galaxy ever identified, providing evidence that massive stars were forming and dying in spectacular explosions even in the very early universe. Protoplanetary disks in detail. Webb has transformed our understanding of protoplanetary disks, the rotating disks of gas and dust that surround young stars and give birth to planets. Previous telescopes could detect these disks, but could only resolve the largest structures within them. Webb reveals gaps, rings, spiral arms, and other features in stunning detail. Features caused by the gravitational influence of planets already forming within the disk, carving out lanes of cleared material as they orbit. By studying these structures, astronomers can infer the masses, orbits, and properties of forming planets that are too small and too close to their star to be directly detected. Webb is essentially watching the solar system formation process happening around other stars in real time in a level of detail that was unimaginable a decade ago. The Large Magellanic Cloud. The Large Magellanic Cloud is a small satellite galaxy of the Milky Way, located about 160,000 light-years away. It contains some of the most active star-forming regions in our cosmic neighborhood, including the Tarantula Nebula, a vast, luminous cloud of gas and dust where thousands of massive stars are being born. Webb has imaged the Tarantula Nebula in extraordinary detail, revealing previously unseen features, delicate filaments of gas sculpted by stellar winds, embedded protostars invisible to previous telescopes, and the remarkable interplay between the radiation from massive young stars and the surrounding material they are slowly destroying. It is one of the most complex and beautiful astronomical objects in the sky, and Webb has shown us more of it than we have ever seen before. Jupiter, up close. Webb was designed for deep space, for galaxies billions of light-years away. But it has also turned its gaze on the planets of our own solar system with striking results. Its images of Jupiter revealed the planet's atmosphere in extraordinary detail. Auroras glowing at the poles, the great red spots swirling in infrared light, thin rings that were barely visible to previous instruments, and even faint moons in the background. But Webb's most scientifically valuable Jupiter observations involve spectroscopy, breaking the light from Jupiter's atmosphere into its component wavelengths to measure the abundances of different molecules, the temperature at different altitudes, and the circulation patterns that drive the planet's famous banded appearance. Webb gave us Jupiter not as a distant striped ball, but as a dynamic, three-dimensional atmospheric system. Saturn's rings in infrared. When Webb turned its instruments on Saturn, it captured something unexpected. In certain infrared wavelengths, the planet's famous rings appear dramatically different from how they look in visible light. The rings glow with their own infrared emission, and different parts of the ring system show different temperatures, reflecting the varying compositions and sizes of the ice and rock particles that make them up. Webb also detected seasonal changes in Saturn's atmosphere. The planet has a year that lasts 29 Earth years, and its northern and southern hemispheres experience different seasons. Webb's infrared sensitivity allows it to detect these seasonal changes in atmospheric chemistry with a precision that no previous telescope could achieve. Neptune's rings. Neptune, the most distant planet in our solar system, has a ring system that is extremely faint and difficult to observe. In Webb's first image of Neptune, released in 2022, the rings appeared with a clarity that stunned astronomers. Thin, bright arcs against the blue-tinted disk of the planet, sharper and more detailed than anything previously captured. Webb also revealed Neptune's moons with exceptional clarity, including Triton, a captured Kuiper Belt object orbiting backwards around the planet, with a surface covered in frozen nitrogen and methane that reflects so much sunlight it appears brighter than Neptune itself in infrared light. It was a reminder that Webb's extraordinary capabilities extend across our entire solar system, not just to the distant universe. Reading the chemistry of icy moons beyond Europa, Webb has been mapping the surface chemistry of several icy moons in our solar system, Ganymede, Callisto, and Enceladus among them. Saturn's moon Enceladus is particularly fascinating. Webb detected a vast plume of water vapor shooting from Enceladus's south pole, ejecting material that feeds Saturn's outermost ring. The plume is so large that it dwarfs the moon itself. Enceladus is only about 500 kilometers in diameter, yet its plume extends for thousands of kilometers into space. Webb's infrared spectroscopy of this plume revealed the presence of organic molecules, carbon-containing compounds that are the chemical building blocks that life as we know it requires. Webb did not find life, but it found the ingredients. 25 years in the making. The James Webb Space Telescope was not built quickly. Its development began in the late 1990s, following a recommendation by a committee of astronomers who recognized that the next great advance in space astronomy would require a large, cold, infrared telescope operating far from Earth. The project was officially approved in 2003. It faced multiple delays, cost overruns, and technical challenges that tested the patience and determination of everyone involved. The final budget was approximately $10 billion, far exceeding original estimates. It involved over 20,000 people from 17 countries, working across hundreds of organizations. And when it finally launched on Christmas morning 2021, more than 20 years after development began, every one of those people, every engineer, every scientist, every technician who had spent part of their career on it, knew that what had launched was not just a telescope. It was the greatest scientific instrument ever built by human hands. How long Webb will last? Webb was designed for a minimum mission lifetime of 10 years, but the launch was so precise, requiring less fuel to reach its orbital position than worst-case scenarios had planned for, that the telescope arrived at its destination with significantly more propellant remaining than expected. This extra fuel is used for the periodic orbital corrections that keep Webb in its proper position at Lagrange point 2. The fuel savings from the precise launch mean that Webb could potentially operate for 20 years or more, twice its designed lifetime. Every additional year of operation means more observations, more discoveries, more questions answered, and more new ones raised. The telescope that took 25 years to build may observe the universe for 20 years or longer, an extraordinary return on one of the largest investments in the history of science. Webb cannot be serviced. One of the most significant differences between Webb and its predecessor Hubble is that Webb cannot be serviced. When Hubble was launched in 1990 with a flawed mirror, NASA was able to send astronauts to correct it on a spacewalk. Webb, orbiting 1 million miles from Earth at Lagrange point 2, is far beyond the reach of any crewed mission. This means Webb had to work perfectly from the moment it launched. There were no second chances, no repair missions, no replacements. Every component had to be designed with extraordinary reliability, because a failure of almost any critical system would mean the end of the mission. The fact that Webb has been operating successfully for years, completing thousands of observations, making hundreds of discoveries, is a tribute to the engineering excellence of the thousands of people who built it. The colors are not real, Webb observes in infrared light, wavelengths that are invisible to the human eye. When you see a Webb image, the colors you are looking at are not the colors a human eye would see if it could travel to that location in space. Instead, they are assigned by image processors at the Space Telescope Science Institute, who map different infrared wavelengths to different visible colors in a way that makes the scientifically important features most visible and aesthetically meaningful. Shorter infrared wavelengths might be mapped to blue, longer ones to red. The choices are both scientific and artistic. The result is images that are simultaneously accurate representations of real physical phenomena and breathtaking works of art. Windows into a universe that no human eye has ever seen directly, rendered in colors chosen to make its wonders comprehensible. Webb and Hubble together. Webb and Hubble are not competitors, they are collaborators. Hubble observes primarily in ultraviolet and visible light, the wavelengths that Webb largely cannot see. Webb observes in infrared, the wavelengths Hubble cannot fully access. Together, they cover a vast swath of the electromagnetic spectrum, and many of the most scientifically productive observations involve combining data from both telescopes. The observations of Glimpse 17775, the little red dot, required data from both Webb and Hubble to fully characterize the object. Webb providing infrared spectroscopy, and Hubble providing ultraviolet and visible data that revealed the host galaxy surrounding the little red dot. Two telescopes, built decades apart, working together to solve a puzzle that neither could solve alone. The universe is not finished surprising us. After nearly 4 years of science operations, Webb has made hundreds of major discoveries, published thousands of scientific papers, and fundamentally changed our understanding of the universe across almost every area of astronomy it has touched. It has found galaxies that should not exist, black holes that grew too fast, chemistry on worlds orbiting other stars, structures in stellar nurseries that were hidden from every previous instrument, and visitors from other solar systems carrying chemical fingerprints of worlds we will never visit. And yet, astronomers who work with Webb every day will tell you the same thing. The most surprising discoveries are probably still ahead. The universe is vast, and Webb has barely begun to survey it. Every observation has the potential to reveal something that nobody predicted, something that changes everything. The universe is not finished surprising us, and Webb is not finished looking. And that brings us to the end of tonight's journey through the universe as seen by the most powerful telescope humanity has ever built. 50 facts, 13 billion years of cosmic history, and a golden mirror floating silently 1 million miles from Earth, still looking, still finding, still rewriting everything we thought we knew. The universe is vast beyond comprehension, and yet, somehow, we built a machine capable of seeing almost to its beginning. We pointed it at the darkness, and the darkness answered. If something in these stories sparked a sense of wonder in you tonight, hold on to that feeling. It is the most human thing there is. There is more waiting for you on this channel. Every week, a new journey. Every journey, a new reason to be amazed by the world we live in. Sleep well, fellow explorer. The cosmos will still be here when you wake up, and Webb will still be watching.